All right, so let us continue. It's great pleasure to introduce to you Enrique Becerra from IMSA. That's going to speak to us about the string spectrum of orbifolds. Please, Enrique.
Thank you. So I'm really glad to have the opportunity to speak here today.
The microphone is not working. Yeah.
Yeah. Yeah. So I would like to speak about some work in progress in collaboration with Professor Lupi and Professor Ernesto. And okay, so let me just say some words about the spectrum of hypersurface singularities, and this is kind of a powerful and somewhat still mysterious invariant of hypersurface singularities. For instance, there is a classical result due to Barchenko, which states some bound for the number of possible ordinary double points which can occur in a hypersurface singularity, which is stated in terms of the properties of this spectrum introduced by Steenbrink as an invariant of hypersurface singularities. And the aim of this talk is to introduce some global version that we are working on of the spectrum of singularities in the context of varieties with terminal singularities, and also for the case of orbitals in an stacky setting. Okay, so we will define two different notions of this global version of the spectrum, as I say, and moreover, we also state some relation between these two notions by a sort of mathematical correspondence between them. Okay, so let me just, in order to state the context, without some basic facts and notations about the spectrum of isolated hypersurface singularities. So let's start with some polynomial map f in f+1 variables, and I will consider the corresponding singularity given by the germ of this map around the origin of this finite space. And so we can define the corresponding Jacobian algebra, which is given in terms of the partial derivatives of this f. And the dimension of this algebra is called the multiplicity, or the Milnor number of the singularity. And it is the case that this number is finite if and only if it is an isolated singularity. Okay, so moreover, we can always restrict the domain and codomain of this map in order to find a good representative of this for this germ of singularity in such a way that what we get is if we take a small enough puncture disk around zero, then it will produce some infinitesimal vibration, which is called the Milnor vibration associated with the singularity. Okay, so in the case of isolated singularities, then we take any point of this puncture disk, then the fiber is called the Milnor fiber of this vibration, and is homothetically equivalent to a bouquet of spheres of dimension n in this case. Okay, so moreover, we also have we have this Milnor vibration, and we can consider the monodromy operator, which is you can for instance take the constant local system on this base P, and then you can take the Heidegger direct image of these local systems, which will produce a local system over the contour disk in such a way that the fiber of each point is given exactly by the middle topology of this XE of the middle fiber. Okay, so once you have defined this local system, then you can produce a holomorphic bundle by taking the transfer product with the sheaf of holomorphic functions on the contour disk, and at the end, you have some holomorphic bundle and a local system in such a way that the local system is given by the parallel transport of the associated connection, flat connection, which is the Gauss-Manning connection. Okay, so in particular, we have a reaction of the fundamental group with some point T in the contour disk. So this is just homotopically equivalent to a circle. And then there is a monodromy operator acting on the homology of the Milnor fiber. Okay, so moreover, this is a classical result of the monodromy theorem, which says that this monodromy operator is quasi-unipotent. So this implies in particular that the eigenvalues of this operator are all of them roots of unity. Okay, so moreover, there is also some additional structure on the homology of the Milnor fiber, which is given by a mixed code structure, which is so this because it was proved by Steenbrink that there is a mixed code structure in the homology of this Milnor fiber, homology of Milnor fiber, and this additional structure allows us to take specific logarithms of the monodromy eigenvalue. So you take some monodromy eigenvalue, then this is a root of unity, which is given by programming right down as an exponential on that type. So you can choose using the mixed code structure, the filtration of the mixed code structure. You can choose some specific values for the logarithms, which are right there as lambdas. So these lambdas are rational numbers, these are roots of unity, and at the end, what you get is some collection of rational numbers which occur with certain multiplicities. So this is by definition spectrum of the singularity. This is collection of this multi-set of rational numbers, and moreover, we can organize this the information given by these numbers into a polynomial like this. So the spectral numbers are hours on this formal variable t, and this is the spectral polynomial associated to the singularity. Okay, so this is the sort of invariant that is the spectrum, and we would like to construct something similar. Not in a local setting of the germ of singularity, but for global singular varieties or orbifolds in other for singular varieties and also for the case of orbitals. Okay, so some basic properties of the spectrum are here in this slide. So these spectral numbers lie in some branch, which is bounded by -1 and n, which is the dimension of the hypersurface in this case. And well, there are some other symmetry properties as well as this kind of negative property for the spectrum when you consider two separate polynomials in different variables. So using these kind of properties, you can compute in some cases the spectrum out of the particular polynomial that you start find singularity. Okay, so moreover, there is also some generalizations of the notion of the spectrum. So this notion of the spectrum is in this mixed code structure is for hypersurface, for the case of hypersurface singularities, but there are some generalizations which works whenever you have some closed subvariety embedded in a smooth variety. So by considering some so you consider the normal zone of this subvariety and using this and something called the other specialization functor, which generalizes. So if we take, for instance, a codimension 1 subvariety, then this is just a line bundle. The normal bundle is a line bundle. And at the end, what you get using this kind of approach is something called the nearby cyclic complex. So this generalized and nearby cyclic cycle complex in such a way that you can produce at each point of the subvariety some spectral polynomial, just as in the case of hypersurface singularities. And if you use this approach in the case of hypersurface singularities, then this recovers the Steenbrink spectrum. So now let me explain how we can try to define the spectrum not for an embedded singular variety, but for a variety with certain type of singularities. So our approach is or fits inside the formalism of something called stringy invariance. So stringy invariance was originally defined in the context of Hodge numbers by Batilev in order to define a correct version of the Hodge numbers for singular varieties in the realm of mirror symmetry. And this was later further generalized and this is and that expands into the theory of motivic integration. But in any case, let me start with some singular variety S. So I will take a resolution of singularities, a log resolution of singularities, so that the exceptional locus of the resolution is supposed to be a simple and normal crossing divisor. And I will consider singularities such that the relative canonical divisor, which is given by this difference between the canonical divisor on the resolution minus the pullback of the canonical divisor on X, can be split into irreducible components with certain multiplicities A, which are called discrepancies. And I will assume that these discrepancies are non-negative. So in that case, you can produce some stratification by closed strata, by some open strata like this. You see the intersection for some finite subset J of this index set, which is indexing the reducible components. And using these certifications, you can attach the spectrum or a spectral polynomial using the this generalized version for the spectrum of embedded singular varieties in order to produce some spectral polynomial like this. So this expression, which appears right at the bottom of the slide, is inspired in some sense in something called the motivic nearby fiber, which was defined by Dennett and Loescher. So Dennett and Loescher defined they start with some hypersurface singularity, and then out of this data they produce some element in a suitable defined Rothenburg ring of varieties in such a way that when you take the Hodge realization of that element, then this you can extract out of that the Steenbrink spectrum of singularity. So this is inspiration for this global version of the spectrum. So this works for, or this is supposed to work in the global setting for varieties with this kind of terminal singularities, but we also want to define a suitable global version of the spectrum, not for varieties with singularities, but for orbifolds, in the sense where we are considering, or when I say orbifold, I mean a Link-Mumford of the complex numbers in this case. So in order to being able to define corresponding global version of the spectrum in the setting of orbitals, it is more amenable to use another way to encode the monodromy and spectrum of this data into an algebraic object, which is called Becerra lattice. So again, we can start with some polynomial map like that. And out of this map, you can construct a model in that form by taking this quotient of space of top differential forms. So it turns out that this is a free model over the ring of formal power series in this variable, which is thought of as a kind of a uniformizing parameter around the puncture disk. And well, there are some structure that you can load this object with some additional structure in such a way that that at the end what you get is something called the model over the ring of differential operators on this formal. These are convergent power series, non-zero. And the point is that the resulting D model that we obtain that way, which is sometimes called the Gauss-Manning system as the singularity, encodes at the same time the mixed structure of the singularity on the cohomology of the Miller fiber and also the monodromy action. So
back up one slide. What's GSPF? Oh, GSPF is that thing. And then what is the AN plus 1 comma 0? What is that 0?
N plus A plus 1.
Yep.
It's a fine space, and this is germs around zero, around the origin of the fine space. Yeah. Okay, so this is just a way to an algebraic way to encode all this information that will be useful when we define we try to define the spectrum of orbitals. And well, in fact, you can recover, for instance, the spectrum by means of certain Q filtration that this D model has. So this filtration is given in some sense, or is given in terms of the generalized eigenspaces of the monodromy action, which can be written down using the structure of the D model, the Gauss-Manning system, the D model structure of the Gauss-Manning system. And out of this filtration, you can recover the spectral polynomial of the singularity in the case of hypersurface singularities, just as this kind of pointilly series, which takes into so the dimension of the corresponding graded pieces are exactly the multiplicities of the spectral numbers, and these graded pieces are not zero exactly when this lambda is or corresponds to a spectral number of the singularity. Okay. So now, in fact, there is some nice categorical interpretation of the Gauss-Manning system. And the idea is as follows. So let's consider the category that you can construct out of this polynomial f, which is called the category of matrix factorizations of f. And well, matrix factorization is given in this case by a set2 graded projective model over the corresponding polynomial ring in such a way that this is also endowed with an odd operator which squares to f times the identity operator. Okay, so this category, this can be organized into a set2 graded DEG category, which has some. So this kind of object is set2 graded DEG categories appears when the framework of non-commutative geometry. So you can think of this category of matrix factorizations in some sense as kind of a non-commutative space, which is which represents the canonical minor fibers. So this object, this non-commutative space category of matrix factorizations, encodes as well all the information that is relevant in this case, which is the monodromy action and the mixed code structure and all that, this data in a single categorical framework like this. So the point is that when you can recover the Gauss-Manin system out of this category of matrix factorization in the following sense. So if you think of the category of matrix factorization as a non-commutative space, then you can compute the periodic cyclic homology of this space. And in the general philosophy of non-commutative geometry, this is usually thought of as kind of the rank homology of the space. So you have this the rank homology of the non-commutative monofiber, if you want. And it turns out that this periodic cyclic homology can be, though, so if this is kind of a replacement of the rank homology, then you may expect that this comes with some kind of Hodge structure or Hodge filtration or some structure.
Can I ask something? I sort of had this feeling, it's based on this feeling I had that non-commutative geometry is not only non-commutative algebras, but there's some Poincare duality related to word geometry. So you need some Poincare duality to make non-commutative thingies into geometry. So you know where Poincare duality would be here?
No.
I mean, for example, after you form this first ring, doesn't it going falling ring, something like that? Is that a great model? There's a Poincare duality. Isn't there some Poincare duality in the original ring form? In other words, Hogan variety. Anyway, there's some work. I mean, okay.
Well, there is this Hodge filtration with,
But
there is this Hodge filtration with the symmetry.
Well, in this case, what you get is not a filtration, but something
Well, yeah, but this takes
different.
place of Hodge filtration.
is there some duality? There's like zero duality. So see, this has to be in there. Now, control on community geometry. One over. And I vaguely remember these algebras. This is from the 70s when they first came out. It's a Tolle algebra or something which has some duality. They get that in some of them.
Well, yeah. So you may expect to find some kind of a replacement for the Hodge structure on this periodic cyclic homology, and the point is that you can in fact have something like that. So by very general principles, it turns out that you can endow the periodic cyclic homology with the structure of a D model exactly over some ring of differential formal differential operators like that, and this is kind of a replacement for the Hodge filtration in this setting. So this is part of something called the rank part of a non-commutative Hodge structure. But the interesting point here is that the rank part of the non-commutative Hodge structure given by the periodic cyclic homology of the category of matrix factorizations recovers the Gauss-Manin system up to some shift given by kind of a Fourier Laplace transform of these things. Okay, so in any case, you can take the formal completion of the Gauss-Manin system, the Gauss-Manin system associated with the singularity, and this can be identified with the D-model structure, the formal D-model structure on periodic cyclical homology on this category of matrix factorizations. Okay, so I will use this kind of approach in order to define the spectrum of an orbifold. So suppose that you start, and let me suppose that this X, which is it is a proper and smooth orbifold. So this is a proper and smooth linear for a stack of the complex numbers, and we can take some line bundle on this X together with a global section. Okay, so with this triple given by the orbifold, the line bundle, and the section, and the global section, then you can construct just in the same way a corresponding category of matrix factorizations that you can apply the same procedure in order to endow the rank of homology of that thing, of that non-commutative space with the D-model structure of this ring of formal differential operators. So you can prove, or you can state some appropriate regularity conditions on this D-model in such a way that this allows you to introduce some infiltration, just as in the classical setting, in order to produce a spectral polynomial like that. So this is kind of a generalization, a global one for the classical notion of the spectrum. So in fact, this generalizes at the same time the notion of a spectrum in the case of hypersurface singularities. We are considering a line bundle and the corresponding category of matrix factorizations, which correspond to something like a visor or a hypersurface of dimension 1 in this X. But moreover, this also works if you take a very degenerate case when the line bundle is just structure sheaf of X and F is the zero section. So in that case, the corresponding category of matrix factorizations is just the same as the category of Ricci vector bundles on this X.
Frobenius algebra structure. In fact, it's something like Frobenius duality.
Frobenius.
You have an inner product. That's compatible with the structure of that Frobenius model.
Yeah, in this case,
where does that come from? You say it as if it's there, but I mean.
Yeah,
there is a set point.
What?
There is a set point.
There is what?
Set point.
I mean, the Sarah point we know. Well, then it is a nice form.
Yeah. Well, in fact, if you take this the general case, what you get when you compute the periodic cyclical homology of this category of Ricci vector bundles is exactly something called the chain-rank homology of X, the orbifold homology. So the orbifold homology is given by the homology of the inertia orbifold X in this case, up to some grading that you may need to consider. But in any case, yes, this is there is a product in this homology ring, the chain-rank product, which is is kind of a limit of the quantum homology product on X. You take quantum homology on X, and you have quantum product, and when you take the limit, the classical limit, then what you get in this case is the chain-rank product. And out of this chain-rank product, then you can introduce a trace on this chain-rank homology, which gives the Frobenius algebra structure, which yes, it's pointed duality, something like that. Yeah. Well, moreover, the model given by Steenbrink model in this case can be written down in terms of the Frobenius structure, which is quite similar to characteristic theory when you take the intersection form and so you take some resolution of singularities and then you take the intersection form of the exceptional divisor, and out of this you can produce a monodromy operator with this calculations formula. So this something similar is happening here in the case of orbitals. So you can define the spectrum using this machinery. Well, this is for the case of smooth and proper orbitals, but you can extend this definition to include more general minimum for stats. So in order to be able to do that, so let me proceed in the following manner. So you start with the Grothendieck ring of orbitals, which is a ring which is generated by isomorphism classes of the minimum for stacks like that, and you introduce some relations on this thing. Well, you take these relations, which are given by taking those pieces of x like that. So this is additive in that sense, and we also need to impose some extra conditions. So, for instance, the product is given by the Cartesian product of varieties, and we also need to include other relations which are related with the, when you take a vector bundle over an orbifold, then you want that the class of the total space of the vector bundle splits as the product of the base times the class of the file. Okay, so moreover, there is also an alternative presentation of this ring. So these kind of presentations are originally proved by Liebner in the case of the Grothendieck ring of varieties. And there is a generalization. This is a generalization of that kind of presentation, which tells you that the ring of orbitals, the Grothendieck ring of orbitals, can be constructed starting with smooth and proper orbitals, and then impose some relations, some low relations like that. So you take an orbifold and then blow up along a smooth suborbifold, and you want that some relation like that take place in this ring. So in fact, you can alternatively use this kind of presentation for the Grothendieck ring of orbitals, and well, if you use this fact, then you can extend the definition of the stringy spectrum starting with the smooth and proper orbitals and using the definition that I just gave. And then, well, you need to verify that the global relations are satisfied by this invariant, which is defined originally in this proper and smooth context. And in any case, at the end, what you get is something called a motivic measure of orbitals. This is just a ring polymorphism from this the ring of orbitals into some ring, which in this case is this ring of polynomial with rational exponents like that. So the definition can be extended to such kind of motivic measure on orbitals like that. And well, so at this point we have two different versions of the for the global, for a global version of the spectrum of a singular variety or of an orbital. So, for instance, if you take some orbital x, then you can consider the coarse quotient space of this x, which under appropriate assumptions is a variety with quotient singularities. So you can apply the stringy, or you can compute the stringy spectrum. So that is the stringy spectrum of the coarse quotient, not of or the orbital. So you can take the stringy spectrum of the coarse quotient, which is a variety with quotient singularities, and you can also consider the orbital spectrum just as in the previous slides. So the point or the interesting thing here is that these two notions agree, and this is kind of a Mackay correspondence between them. So this is in the general setting of stringy invariance, when you consider some stringy invariant and the corresponding orbifold invariant, then you usually try to compare these two things and verify that they agree. So in this case, the Mackay correspondence.
The values of, what are these values is C,
The values of what?
where are the values, the homomorphism, ring homomorphism,
Yeah.
to C?
Yeah. No, it's to this ring of polynomial.
Ring of,
So this is these are the spectral
Oh.
that are the spectral polynomials. So the spectrum are given by the support of these spectral polynomials. So this is just a way to encode the multi-set of rational numbers into a single object.
Enrique, so like this, like, I mean, there's an correction, it's saying that this thing expect has nothing to do with the moment.
from being century.
Yeah. Yes, this has to do with chain rank homology, right? And this is so you need to you can write down this in terms of the Frobenius algebra. Yeah.
I see, sorry, I missed this.
Okay,
So
so
R is polynomials and T is blank.
yeah, R in this case are
Yeah, I don't know like the brackets, I mean, I've always used that with brackets.
it's just a notation that I use to state that these are polynomials in some formal variable with a rational exponent.
Polynomial expressions were
Or
rational.
polynomial expressions,
Just polynomial.
a polynomial expression, yeah. There are just finitely many. Okay, so this kind of mechanical correspondence can be proved using something called the localization principle for orbifold theories, which appears in the work of Professor Ernesto and his collaborators. And in this particular setting, this localization principle states that when so you can define something like something called the motivic volume of an orbifold, which is an element. So you start with some orbifold and then you produce some element on the locally on a locally ring of orbifolds localized at this or like adding this formal roots of the Lipschitz motif like that. So this volume belongs or lives in this motivic ring and R. And it is the case that this volume can be decomposed into by taking into account these the connected components of the inertia orbifold. So you have the orbifold X, you have its inertia orbifold, and each connected component of this inertia orbifold is sometimes called the twisted sector on this of X, and so there are so the volume splits in terms of contributions of the twisted sectors like that. So this omega alpha that appears here is something called the degree shifting number of the corresponding twisted sector, and using this kind of localization into the twisted sector, then you can prove the very general form of Mackay correspondence, and in particular, you can prove this Mackay correspondence for the spectral polynomial. Okay, so a very nice example of these things is given by the case of Kleinian surface singularity. So you can take some finite subgroup of SL2C, and these groups are classically so they was classified by Klein, and it is the case that such finite subgroup is given by a cyclic group or a hedral group or a binary polyhedral group or for some platonic solid. So you can take the corresponding quotient variety of this G acting in the complex plane. And in fact, this quotient, so this has an isolated singularity at the origin. And moreover, you can also realize this quotient as a hypersurface. So in fact, there are some polynomials, invariant polynomials in this ring of polynomials into variables U and V in such a way that they satisfy a single relation. In such a way that the corresponding hypersurface in three-dimensional finite space is exactly or can be identified with this quotient singularity. So this is classical. And so, for instance, you have some classification of these things according to the type on the AAD classification. So in each case, you have the corresponding group, which can appear as a subgroup of SL2C, and the associated equation which satisfy this, or so you can realize the corresponding singularity using the corresponding equation in this table. So, well, you can also compute the spectral numbers of these simple surface singularities, and well, a question, a natural question could be the following. So you can define the spectrum using the Steenbrink spectrum, the classical Steenbrink spectrum of singularities using this equation, these explicit equations which define these quotient singularities. But you can also try to, or you can ask if there is some way to realize the spectral numbers just in terms of the corresponding orbital. So you have the realization as a hypersurface singularity, but you also have this realization as a quotient singularity, like that. So the question is if there is some way to extract the spectral numbers directly out of the quotient orbital. And in fact, using this Mackay correspondence within the spectrum, the answer is yes. So you can compare the spectrum of the corresponding hypersurface singularity with the spectrum of the orbital as I defined previously. And well, it turns out that these two spectral numbers agree. But moreover, the spectral numbers of the orbital, of the quotient orbital, are given in terms of chain-rank homology of the quotient orbital. But in this particular case, chain-rank homology can be identified up to grading, of some grading that you need to consider, as the representation ring, or in terms of the complexified representation ring of G, which is the space of class functions on G. And well, in principle, you can compute the spectrum out of this thing, and so this will, you can try to explain the origin of the spectral numbers directly in terms of the representation theory of G.
Excuse me. Explain what, recall what CR means, homology sub CR.
It's the chain-rank homology. Chain-rank homology.
Oh, two guys names.
Yeah. Okay. So, well, let me just finish with some potential application that we have in mind. And well, there is this notion of elliptic genus of a singular variety. So originally, elliptic genus was defined as a co-producing invariant of manifolds in such a way that, well, there is a characterization of those genus which satisfy that kind of multiplicativity property. So a genus is a co-producing invariant, so you define, or you have defined a ring homomorphism out of the ring of probabilism classes like that. And note that there is some similarity between this multiplicativity property and the property of the corresponding multiplicativity property for the motivic measures. So this was pointed out by Professor Ernesto and Professor Bernardo. So, well, the point is that there are some genus, some genera which satisfy this kind of multiplicative property with respect to bundles whose fibers are spin-manifold. So when there is this, when these multiplicativity properties are satisfied by a genus, then it turns out that this holds true if and only if the logarithm of the genus, which is given by this formal power series, is in fact an elliptic integral of that type. So this is the classical notion of elliptic genus, but this was well, later extended by Hirsebruch, by the work of Hirsebruch to the realm of complex manifolds, and later on it was also generalized by Gover, by the work of Gover and Borisov to the case of singular varieties. In a similar way as we define the spectrum, in the sense that they define a version for the elliptic genus for varieties with terminal singularities, and they also define the elliptic genus of orbifolds, and then compare these two things and they prove a high correspondence for the elliptic genus. The point, or some very interesting observation that Borisov and Gover made, is that well, you can define the elliptic genus of a hypersurface singularity given by some polynomial map F like that. But it turns out that when F is weighted homogeneous, then the spectral numbers of the isolated singularity, if this is an isolated singularity, can be, or they show up out of the elliptic genus in this kind of limiting situation. So the elliptic genus in this case is an invariant of singular varieties, and this invariant is given by some holomorphic function, or can be represented by some holomorphic function in two variables, q and y, satisfying some modularity properties. And the point is that when you take the limit of this invariant as q goes to 0, then this recovers. This is basically the right hand side is basically the spectral polynomial of the singularity. So it's a polynomial in y whose exponents are given by the spectral numbers of the singularity, and up to this factor at the beginning of this of the right hand side, then the elliptic genus recovers in this limit the spectral numbers. So well, we conjecture that something similar happens in the context of the global version of the spectrum that we introduced. So the idea is that in the case, so if you start with an orbifold, then you can compute, or you can produce the orbifold elliptic genus of this orbifold, and you can also produce the global spectrum of the orbifold. And the conjecture is that something like this limiting formula occurs also in this global setting, that the spectral numbers of the orbifold as we define appears as the limit of the orbifold elliptic genus of X. And we have some theoretical reasons to believe in this kind of that this is true, and well, these are based on some ideas of Professor Ernesto about the relevance of the formal double space on what you define the genus of an orbifold, and also well, in fact, the formal loop space of the orbifold X, in fact, is behind the definition of the stringy spectrum. So When you find this, the orbifold spectrum, then this is given in terms of the chain rank homology, and the chain rank homology is given or it's related with the inertial orbifold of X, and this inertial orbifold is in fact related with the formal loop space of X. So in some sense, when you start with the informal double loop space, then you can take some kind of truncation for one of the, let's say, the formal cycles of this formal torus, and at the end, you should get some expression like that, like the spectrum of orbitals and the orbital that it begins that way. Okay, so thank you for your attention.